In this video, we are going to look at how to write proofs by induction. I'm going to take you through the methodology and then we will do these 4 examples. Particularly if you've never seen induction before, take a moment to pause on these 4 examples, read each of the statements that we're going to prove, and see if you can recognize when a proof by induction is an appropriate method to try. What I hope you noticed in these 4 examples is that each of these is a formula involving positive integers. For example, the first one tells us that if n equals 5, then 1 plus 2 plus 3 plus 4 plus 5 is 5 times 6 divided by 2, or 15. The second formula tells us that if we compute the factorial of any positive integer, it's less than or equal to that integer raised to itself. For a quick example, 3 factorial is 3 times 2 times 1, so that's the product of consecutive integers. And that is indeed less than or equal to 3 cubed, which is 27. Bernoulli's inequality, on the other hand, tells us that if we have a fixed value of x, which is at least -1, then 1 plus x to the n, where that's a positive integer, is greater than or equal to 1 plus n times x. So for example, 1 plus x squared is greater than or equal to 1 plus 2x. And then for fun, to give you an example which looks a little bit different, we will prove a formula that you can use to compute the determinant of an n by n upper triangular matrix. So there, what's key is that the dimensions of the square matrix are being described as n by n. So you certainly cannot use a proof by induction in every situation in mathematics. It's used for formulas which involve positive integers. So that bold-faced n symbol that you can see on the second and third line, that stands for the set of natural numbers. Just remember that's positive integers. To talk through the methodology behind writing a proof by induction and to do the first 2 examples, what we're going to use is this notation P of n. I don't actually use P of n when I write a proof by induction, but I think it's helpful for the setup. So in a moment, I will show you how to prove a statement P of n is true, where for number 1, P of n would be the statement 1 plus 2 plus all the way through n equals n times n plus 1 divided by 2. So it's that algebraic statement, and we are interested in showing that P of n is true. Here's how we'll proceed with induction. I like to imagine induction as climbing the rungs of a ladder. Each rung is a positive integer. So you can think of the bottom one as, say, the number 1, and then 2, and then 3, and then 4. We will show a formula is true for these discrete whole numbers. The first step is to prove what we call the base case. That is to show that the statement P of 1 is true. It's almost always P of 1, but depending on the context, it could be P of 0 or P is 2, but whatever it is, you need to have a bottom rung for your ladder. Typically, step 1 is almost trivial algebra. You will see 4 examples. The next step is where I think induction is really beautiful. What we do is we state what's called the inductive hypothesis. There is no proof in step 2. All you do in step 2 is you make a statement, and I've given you here the typical form for it, so it almost always sounds exactly like this sentence here. Suppose that for some k from the set of natural numbers, P of k is a true statement. So if we think about our ladder, in step 1 we prove the base case is true, but now I'm imagining that for some k out there, I also know that P of k is true. So you want to imagine that k is some selected finite number for which you know that P of k is true. The language of for some here is key rather than for all. So k is not representing every natural number, k is specific. So I'm imagining that there's some rung out there where I know that P of k is true, and then what we do is move into what we call the inductive step. And this is where it feels like you do the most math. What you do is assume that the inductive hypothesis is true, and you use that to prove that you could climb to the next rung on the ladder. So you show that if P of k is a true statement, then P of k plus 1 is also a true statement. And that's it. So proof by inductions always follow these 3 steps. This is regular induction. There's a type of induction called strong induction, but even strong induction also has a 3-step process. Let me demonstrate why this 3-step process proves that the statement is true for all natural numbers. In step 2, we did not specify a value for k, but we imagined that k had a fixed value. So again, k was something specific. When we think back to our base case, though, we have already found a k for which the formula is true. Well, if P of 1 is true, then P of 2 is also true. So now I know the formula holds when n equals 2. And then we just start over. So we climb from the second rung on our ladder to the third one. If the formula is true when n equals 3, then it's true when n equals 4, and then it's true when n equals 5, and then it's true when n equals 6. And basically we build up our ladder so that for any positive integer you like, you could build up to it. Therefore, the formula is true for any choice of positive integer. So let's summarize what you have to show when you do a proof by induction. The first step will be to show that p of 1 is true. You have to have a bottom rung to your ladder from which you start climbing. Then step 2, you don't prove anything, you just make the statement that for some k out there, p of k is true. And then step 3, which is typically the longest, you show that if p of k is true, then p of k plus 1 is true. So the first step gives you the bottom rung of your ladder, and then steps 2 and 3 combine to say that you can climb the ladder. So we can climb to the second rung, the third rung, the fourth rung, etc. For the first 2 examples today, I'm going to make this 3-step scrapwork very clear, but you will see that proof by inductions are quite formulaic. So for examples 3 and 4, I will actually go straight to writing them. But even as we write up the formal proofs, the 3-step process should be apparent to the reader. So proofs by induction should always be clearly broken down into 3 steps. Okay, let's start with this example, the sum of consecutive integers formula. We are going to prove this first by induction, then we'll have a little conversation about this formula. So first, just to make sure we understand it, if n equals 4, we have 1 plus 2 plus 3 plus 4 is 10. That's the left-hand side of this equality. And on the right-hand side, we have 4 times 5 divided by 2 is also 10. Okay, I'm convinced, but we still have to prove this. Okay, so our statement P of n that we are going to assess with the 3 steps is that the sum of the first n integers is n times n plus 1 divided by 2. The question is this a true statement for all n? Well, let's start by showing that it's true when n equals 1. I've written down here a very simple equality. On the left-hand side, if n equals 1, I just have a single number, 1. And on the right-hand side, I have 1 times 2 divided by 2, which is also 1. This kind of arithmetic is common in the base case, so it's almost always a very, very simple algebraic statement. Moving on to number 2, what we want to do is suppose that for some k from the set of natural numbers, p of k is true. Our proof will say 1 plus 2 plus all the way through k is k times k plus 1 divided by 2. Step 2, it's really key that you do this correctly. It's just a statement. So this statement that I've written down will go directly into our proof as is. I want to make a note here, and that is that I encourage you to use this letter K rather than N. It's not required, but the formula at the top is stated for any N. So we think of N as a variable, and it could be any natural number. And in step 2, I really want to emphasize that I have a fixed K. So I like to switch letters so that I feel that K has a specific value. Also, make sure to include the phrase for some rather than for all. If you were to write, suppose that for all k, p of k is true, then you are literally supposing the formula is already known to be true. That's actually what you're trying to prove. If you also didn't write for some and wrote instead, suppose that 1 plus 2 plus all the way through k equals k times k plus 1 over 2, I think it's implicit that the formula holds for all k. So really make it clear to the reader here that k is special. This is the language I use. You could also say something like, suppose there exists a k from the set of natural numbers for which 1 plus 2 plus all the way through k is k times k plus 1 divided by 2. But basically, if there's a quantifier in your second step, it should be the existential quantifier and not the universal quantifier. Okay, let's go through step 3. I want to prove p of k plus 1 is true. So this is going to be a proof. I recommend you always start by just writing down the left-hand side. So here, the left-hand side of p of k plus 1 is the sum of the consecutive integers from 1 through k plus 1. Notice that I've included the kth term in my expression, and that's because it looks just like the left-hand side of our hypothesis in step 2. In step 3, we are assuming this inductive hypothesis from step 2, which means I can replace the sum that I've highlighted with the quantity k times k plus 1 divided by 2. You should always have this kind of procedure. So I've written out the equality for pk plus 1 explicitly, and then I have identified how the hypothesis comes into it. That I can replace the sum from 1 through k with k times k plus 1 divided by 2 is our assumption from step 2. And now I'm going to show that adding k plus 1 to that will lead me to the correct place. This is just algebra. I'll give you a moment to read through that. What I did on the second line is factor k plus 1 out from both the highlighted part and the not highlighted part. But there are other ways you could have done that. You could have just gone straight to a common denominator. Whatever algebra you do, it should lead you to the expression k plus 1 times k plus 2 divided by 2. And that is the correct right-hand side for the statement p of k plus 1. I'm now going to take this scrap work and put it together into a formal proof. It's often the case that students will give me proof by inductions that look exactly like what we've written down, maybe without the colored boxes and the notes I've made. But for me, when I write a formal proof by induction, I actually do not use that P of n language. Here's how I would phrase this. I open by telling my reader that this is going to be a proof by induction. The language on n is not always included, but it's also not unwelcome. For the base case, and then I just put my base case computation. While I don't use the language P of 1 here, I do explicitly say that this is the base case. And then I like to say next to tell the reader that I'm going to the second part of a proof by induction. And then it's literally the phrase I had before. So for some k out there, we know the statement is true for that k. And then again, I lead them to the next part of the proof, the inductive step. And I wrap it up pretty quickly. So here's the proof that I would do for this formula. I could say perhaps a little bit more going into the inductive step, but the idea is that a proof by induction follows the same three-step process, and this is something that's universal, meaning that if I tell the reader it's a proof by induction and the 3 steps are very clearly laid out, then they should be able to follow this. I just said that this is the proof I would write for this formula, but there are other ways to prove this that I'd like to share with you for a moment because I think they're fun. And the first one has a historical note. So one day, the mathematician Gauss was a young boy. I'm not sure how old he was, but the story is that he was in his class in school, and the teacher wanted to give the students an exercise that would take up some time. So the teacher told the students to add all of the numbers from 1 to 100. Now, if I were a young child in that classroom, I would have said, okay, 1 plus 2 is 3, 3 plus 3 is 4. No, I've already made a mistake. 3 plus 3 is 6. 6 plus 4 is 10, et cetera, et cetera. I think that's what the teacher expected the students to do. But Gauss, on the other hand, was Gauss. So what he did was come up with a clever way to pair the numbers from 1 to 100. According to the traditional telling of the story, the way he paired them is a little bit different than what I'm about to give you. So this is a variation on his approach. Imagine we wrote the numbers 1 through n, and then n through 1 as I've arranged them here. If I want to just add up the numbers in the left column, but I could instead add all of the numbers in both columns, then I divide by 2 to get simply the left column. So could we actually add up both of these columns in a way which is more efficient than trying to do my childhood approach? What Gauss recognized is that you could pair the numbers to form sums of the form 1 plus n. So if I read across the rows, each of these rows adds up to 1 plus n. And then how many rows do I have? N of them. So very quickly, we can sum both of these columns together to say that we have n copies of n plus 1. In other words, we have the product n times n plus 1. And that is just double what we need for the first column. So the sum of the first column would be n times n plus 1 divided by 2. Applying that to the formula for n equals 100, you could say the sum of the numbers from 1 through 100. Arranged this way, you would have 100 rows adding up to 101. That's twice what you need. 100 times 101 divided by 2 is 5,050. So that is perhaps a more satisfying way to prove this formula. Let me take you through another interpretation of the sum of consecutive integers formula. This is a little bit of a detour, but we'll go back to induction in just a moment. Consider this scenario. In a room of 30 people meeting for the first time, how many handshakes will occur? So everyone has to shake hands with everyone else and nobody shakes their own hand. Well, let's say we number the people 1 through 30 and we have them shake hands chronologically. So person 1 goes around the room and they shake everybody else's hand. That means we would send person 1 around and they would do 29 handshakes. And then maybe they go sit down in the corner. Person 2 steps up And since they've already shaken person 1's hand, they will shake hands with 28 people. And then they go sit down in the corner. Person 3 steps up and they will shake hands with 27 people. And we keep doing this until we get to person 29 has 1 handshake left. And then person 30 says, everyone's already shaken my hand, so they won't shake anybody else's hand. So like this, we've arranged all of these introductions. It doesn't sound like a particularly fun gathering, but we recognize in this way that the total number of handshakes will be the sum from 1 to 29. That's 29 times 30 divided by 2, which is 435. There I've used the formula that we've proven, but there's another way you could think about this number. To compute the number of handshakes that will happen is to compute what we call the binomial coefficient, 30 choose 2. This is a specific binomial coefficient. It's part of a larger family of numbers that you can learn about in combinatorics. We write 30 choose 2 like this. And the computation is 30 factorial divided by 30 minus 2 factorial times 2 factorial. So you can see how those numbers on the left go into the formula on the right. If you actually expand that fraction, it will simplify to 30 times 29 divided by 2 times 1. And what this binomial coefficient 30 choose 2 means is of 30 people, how many ways are there to choose 2? In other words, in a room full of 30 people, how many ways could you pair them up for a handshake? And that's going to compute the same number, 435. Okay, I've gotten a little off topic now, so let's go back to induction and prove our second example is true. So here we have n factorial, that's the product of consecutive integers up to n, is less than or equal to n to the n. And again, to experiment with this formula, you could plug in n equals 3. 3 factorial is 3 times 2 times 1, that's 6. That is less than or equal to 3 cubed, which is 27. I always recommend testing a formula on a number or two just so you understand it. Okay, so our property this time is an inequality. P of n will represent n factorial is less than or equal to n to the n, and we want to prove that that statement is true for all positive integers n. It's the exact same 3-step process. Our first step is to plug in n equals 1. 1 factorial is 1, which is actually equal to 1 to the 1. But if it's equal, then it's also less than or equal to, so that's what I'll write down. Step 2, again, there's nothing to prove here. You make a statement. My statements always take the same form. I think consistency reinforces understanding. So I would write, suppose that for some k from the set of natural numbers, k factorial is less than or equal to k to the k. Again, in step 2, you are not claiming that it's true for all k. You are saying that there's some k out there for which it's true. Now, from this inductive hypothesis, we move into our inductive step. I will put up the algebra in just a moment, but see what you can make of this. So just like we did before, you want to write the left-hand side of the statement p of k plus 1. That's going to look like k plus 1 factorial. Stay with that expression. Do not jump straight to the right-hand side of p of k plus 1. Stay with k plus 1 factorial and work with it and see if you recognize how to bring in the assumption from step 2. All right, here's what I did. Starting with the left-hand side of k plus 1 factorial, that's the product of consecutive integers from 1 to k plus 1. Well, if you write out that product, you recognize that you can peel off k plus 1 and write that as k plus 1 times k factorial. And now that's great because we have part of the hypothesis. By hypothesis, k factorial is less than or equal to k to the k. And now from line 2 to 3, you have to make a bit of a step there, recognizing that if I increase the base for the term on the right, we go up in size. So k to the k is less than or equal to k plus 1 to the k. And now I can simplify that product in line 3 to k plus 1 to the k plus 1, and that's exactly where we were trying to get to. That is the right-hand side of p of k plus 1. It's always important to realize how you've brought the hypothesis into step 3. You are not trying to prove step 3 in an isolated situation. You are given a statement that you can and should use in step 2. Okay, now I'm going to rearrange this scrapwork into what I would write as a formal proof by induction of this statement. It's going to sound almost identical to example 1, and that's not an accident. So once again, we proceed by induction on n. For the base case, 1 factorial is less than or equal to 1 to the 1. The base case is almost always a trivial statement like this, but include it. It's important that you establish that the statement is true for the bottom rung of your ladder. Next, we show that we can start climbing the ladder. So I want to suppose that for some natural number k factorial is less than or equal to k to the k. And then with this hypothesis, or using this hypothesis, we find, and then I include my algebra. Before we move on to Bernoulli's inequality, take a moment to read back through examples 1 and 2, and in particular with the third step, I want to highlight a couple of things. The first is that I really spelled out the algebra. I didn't skip steps. Don't skip steps. Make sure your reader sees the hypothesis coming into your computation. So I wouldn't want to write that k plus 1 factorial is less than or equal to k plus 1 times k to the k. Don't make that leap. Bring it in explicitly. And then again, you're proving a formula, and sometimes these formulas are tricky. So don't go from line 2 to line 4. Bring in line 3 where you say, hey, look, if I increase the base, then I can take this inequality to the desired form. With these formulas on integers, I think it's worth really leading us through the computation. So that's my first remark. My second is that if you look at both of the examples we've done and the 2 examples remaining, notice how I started with the left-hand side of my statement and I stayed with that. I brought in the hypothesis and I rearranged terms and I did some simplification until I got to the right-hand side. One of the biggest mistakes I see students make is they try to work with the left and right-hand sides at the same time. Pick a side, typically the left, but doesn't have to be. You could fix the right-hand side and simplify until you get to the left-hand side. That would work, but for me, it's almost always going to be left-hand side to right-hand side. So pick a side like the left-hand side and show that with the hypothesis and with some algebra, you arrive at the right-hand side. So the right-hand side is the destination. Now let's take a look at Bernoulli's inequality. This tells us that for any value of x greater than or equal to -1, 1 plus x to the n is greater than or equal to 1 plus nx, where n could be any natural number. The best way to appreciate this inequality is with a graph. So here the curve on top, the red curve, is the quadratic 1 plus x squared. So here n equals 2. And then the straight line is 1 plus 2x. So what this inequality tells us is that the polynomial 1 plus x to the n sits above the straight line 1 plus nx for any positive integer n, so long as x is at least -1. To the left of x equals -1, the inequality is not necessarily true. To see that, you can plot a few graphs where n is odd. And at the end of the proof, you can take a moment to read through what we did and see if anything would break down if x was, say, to the left of -1. But x is not what we induct on. For one thing, x isn't even necessarily an integer. What we induct on is the integer n. So we will consider this inequality for the same domain of x greater than or equal to -1, and we will climb the rungs of the ladder for n. The proof is going to follow the same 3-step process as our first 2 examples. In fact, I'm not going to do the scrap work this time. I'm going to jump right into the proof. So if you would like, you could take a moment to write out those 3 steps explicitly as scrap work before watching my final proof. Okay, let me put this graph away. For the proof, I'm going to bring in the hypothesis on x. I think it's nice to point that out to the reader. So suppose that x is greater than -1. We proceed by induction on n. For the base case, observe that 1 plus x to the 1 is actually equal to 1 plus x, but I can think of that as greater than or equal to 1 plus x, or 1 plus 1x. Again, the base case always feels like you're stating something obvious, but that's how it is. And notice that I am, again, including the phrase base case specifically so that the reader understands, yes, indeed, this is a proof by induction. Next, taking the reader to the inductive hypothesis. Suppose that 1 plus x to the k is greater than or equal to 1 plus kx for some k from the set of natural numbers. Okay, again, if you haven't worked through this, go ahead and see if you can do the inductive step. Start with the left-hand side, 1 plus x to the k plus 1. In a manner sort of similar to example 2, see if you can peel something off to bring in the left-hand side from our inductive hypothesis and proceed from there. Here's how I did the inductive step. I will put the whole computation up at once. Like with example 2, it amounted to recognizing that 1 plus x to the k plus 1, you could peel off one copy of 1 plus x to break this down into 1 plus x times 1 plus x to the k. Now I have the left-hand side of our inductive hypothesis. So I can replace 1 plus x to the k with 1 plus kx and go down in size. Then I just use algebra, so I expand that out. We have 1 plus kx plus x plus kx squared. Don't skip steps, then gather the middle two terms into k plus 1 times x. And then you just need to recognize that, k is a positive integer. So if I remove kx squared from my expression, we go down in size again, preserving the correct order of the inequality, and we arrive at 1 plus k plus 1x, which is the desired form of the right-hand side of our inequality when n equals k plus 1. So I make a little note there for the reader why I removed the kx squared, why that was a safe thing to do, and then I wrap it up quickly by pointing out to them that the formula holds. This proof follows the same outline as examples 1 and 2, and that's expected because proofs by induction are very formulaic. I think they're fun, but they're formulaic. To do an example which has a slightly different flavor, at least it's not being given to us as just some algebraic expression within, let's prove that the determinant of any upper triangular matrix can be computed by just doing the product of their diagonal terms. So that expression on the right-hand side of the equality means the product A11 times A22 times A33 all the way through the bottom right entry ANN. If you've had linear algebra, that's great. You've probably taken the determinant of a 2 by 2 matrix before. That's pretty fast to do. So I would just experiment with this for a second with a 2 by 2 matrix. For example, this matrix here with rows 5, 2, 0, 3. If I compute the determinant in the normal way, it's 5 times 3 minus 0 times 2, that's 15, and that is indeed 5 times 3, and you see what happened, the 0 wiped out the 2. So the part above the main diagonal. We want to prove that the determinant now for any n by n upper triangular matrix will come down to the same thing, just the product of the main diagonal. Once again, I'm going to jump right into the proof. So we'll start by saying we're proceeding with induction. First, notice that the determinant of a 1 by 1 matrix is just the entry in the matrix. So that is actually my base case. Perhaps I should have written that it's the base case here, but I left that out. But at least I've used the word first here to show the reader that this is the first step in the well-known 3-step process. So for our inductive hypothesis, I will write next, again to indicate to the reader that we've moved on to step 2. Suppose that for some k from the set of natural numbers, the determinant of any k by k upper triangular matrix is the product of its diagonal entries. So that is our hypothesis, that there's some dimension k out there so that a k by k upper triangular matrix will satisfy this determinant formula. To save a little room, I'm proceeding right into step 3 here, but it might be nicer to actually put it on its own line. Now consider any k plus 1 by k plus 1 upper triangular matrix. In order to prove the desired equality, you have to know how to compute the determinant. So assuming that you've seen cofactor expansion before, you'll recognize that as we go along the bottom row, most of the terms in our determinant computation will be 0. So they will vanish because of the zeros on the bottom row. However, when I arrive at that last term, it does contribute to the determinant computation. And how it contributes looks like -1 raised to the row number plus column number for that term. Well, in this case, that's k plus 1 plus k plus 1. Notably, it's an even number because it's twice k plus 1. So the -1 will end up being raised to an even power. We will multiply that with the entry in the bottom right corner, and then multiply that by the determinant that I haven't crossed out. So that's the k by k submatrix that you see in the top left. Do you see where the inductive hypothesis will come into this computation? Well, what we recognize is as we compute the determinant, we have this k by k upper triangular matrix that goes into our cofactor expansion computation. By the inductive hypothesis, we know what the determinant of that matrix is. It's the product of the diagonal entries, but now we're multiplying that product by the k plus 1th diagonal matrix for the original matrix on the left. And that turns into the product of all of the diagonal matrix for the k plus 1 by k plus 1 upper triangular matrix, and we're done. If I weren't limited by the size of my screen, I would put now consider on its own line, just to discretize this proof clearly into the 3 steps. We finished our fourth and final example, but I would like to take a moment just to talk over common mistakes that I see. Sometimes I see a student starting to prove a formula by induction and they've forgotten about the base case. A fun exercise to highlight how important the base case is to revisit what we just did. If it was all right to leave out the base case, then I could falsely prove that the determinant of every upper triangular matrix is 0. You can take a moment to see if you can do that. And therefore, the base case is necessary. We must have the property true on the bottom rung of our ladder. The second remark is a writing remark, and that is that sometimes students overuse the index in throughout their proof. Here's something I see a lot. Suppose the property is true for n, or they may even write n equals n. Now we show that it is also true for n equals n plus 1. And that's just a strange thing to say. So I think I may have taken this exact phrasing from an actual student proof, but I recommend for the inductive hypothesis and step, parts 2 and 3 of your proof, that you switch from the general notion of an index n to a specific integer called k. The third mistake is the most fundamental error, and that is that students, when they're beginning proofs by induction, they often do not correctly move from the hypothesis to the inductive step. I hope in the 4 examples I gave you in this video that it was clear that I started on one side of my desired statement, rearranged the terms on that side to bring in the hypothesis, and then you simplify until you get to the desired right-hand side. Here's what I see sometimes. A student will say, suppose some kind of inductive hypothesis, and then they will take k plus 1 and just plug it into k. So they'll say, oh look, if k goes to k plus 1 on the left, we get the sum from 1 to k plus 1, and on the right, k times k plus 1 will become k plus 1 times k plus 2, and therefore we have the right equality. This is not at all correct. In this statement, you are just renaming the letter. Your inductive hypothesis is true for a specific k. You are saying that there is a rung on the ladder where the property holds. You then must move to the next rung. Here, that movement hasn't happened. A formula being true for a specific choice of k does not mean that you can change k. So this demonstrates a fundamental lack of understanding of how a proof by induction works. Again, revisit the 4 computations that we did in this video, and notice how we started with one side of the property for k plus 1, a new number, and then brought in our hypothesis to move eventually to the other side of the statement for k plus 1. And then the last mistake that I've listed here is really trying to use induction when induction is not appropriate. I call this inducting to infinity. Saying that a property is true for every finite positive integer is not the same thing as saying that a property is true as n goes to infinity, so in some sort of limit. All of the computations that we did today were true for any integer n, but when you say that, every time you pick an n and plug it into the formula, you have picked a finite number. For example, the sum of consecutive integers formula holds for any choice of positive integer. You can add up from 1 to 300 by doing 300 times 301 divided by 2. But by choosing the number 300, I have chosen a finite number. Let me give you some examples. For every finite positive integer n, the finite sum 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared all the way through 1 over n squared is a rational number. And you could prove that with induction. But if I take n and replace it with infinity to get the infinite sum, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and I add up forever, I do not stop at a finite choice of n, then this is a very famous infinite p series from calculus. We know what it adds up to. It actually adds up to pi squared over 6, which is not a rational number. So my property could have been that the finite sum is rational. You could prove that with induction, but you cannot then let n go to infinity include that the infinite sum is rational. For a second example for you to look at, if you take sets of real numbers of the form 1 to infinity, 2 to infinity, 3 to infinity, but then you stop at some finite n, the intersection of all of those sets is non-empty. In fact, it's n to infinity. But, and this is a nice exercise to think through, if you take n and replace it with infinity, so you say, let's take the intersection of all such sets, 1 to infinity, 2 to infinity, 3 to infinity, and we kept doing that forever, the intersection is empty. So be careful anytime you are looking at a statement where perhaps what you're doing does involve positive integers. Like here, the sum is involving terms with j equals 1, j equals 2, j equals 3, etc., but we are working with an infinite number of them. You cannot use induction. Induction works for statements that are true for finite choices of n. It does not extend to infinity, and I will wrap this up there. We have covered basic proofs by induction with these 4 examples and our discussions around them. I will mention that there's another type of induction called a strong induction. I didn't do any examples of that in this video, but hopefully if you read through them after this video, it will make sense to you. A strong induction follows the same 3-step process, it's just your hypothesis is a little bit different. Okay, so this concludes our first look at proofs by induction. Thank you for your attention.